Okay, so as Kevin mentioned, I would like to now offer an example of one way to put some of the principles that you've just learned about into practice using an example project which is effectively a refurbishment of the studio space, what we call the main studio here at Foster and Partners in Battersea. I'm putting a photo of the space as it was previously up on the screen. It's currently a construction site because the refurbishment is ongoing. But one of the things that we were challenged to do as part of this refurbishment work was to propose what we thought was the absolute best lighting that could be achieved in a workplace environment. As you can see here, we have access to ample daylight in this space. We have this large north-facing facade, which is nearly 8 meters tall in glass, mostly unobstructed, so you get an excellent view of the sky. But what we have to do is also provide light for the evening hours, of course. And so one of the things we wanted to do was to reuse actually these fixtures which have existed in this space for many years, since actually around 1990 when the company first moved into it. They were fluorescent tube fixtures with these kind of glare louvers on them, and they function actually quite well. They're very low visibility. They have excellent glare control. They light the space very well. And most importantly, they were perfectly functional, except for the fact that you'd have to replace the fluorescent tubes very often. So one of the big ideas we wanted to do is actually just preserve these fixtures as much as we could and just retrofit them with some modern technology so that we weren't wasting the perfectly good steel and other materials already used in the fixtures, which are perfectly fine. So here you see a photo of a guy retrofitting one of these fixtures with an LED board, a custom PCB with 4 different LEDs on it. You can kind of see here this orange one is a warm white LED at 2700 Kelvin. The cool one here is a cool white LED at 5000 Kelvin. And then there are 2 additional chips here, which are not immediately noticeable, but one of them is effectively a blue LED, which produces a light that peaks at that wavelength that Roger was mentioning earlier, the peak of the melanopic sensitivity curve at 480 nanometers. And another one of those diodes is producing light at 850 nanometers, which is beyond the visible range of light, but on the other side of the spectrum into the near infrared. And I'll come back to that a bit later. And all of this lighting all across the space will be controlled by a weather station up on the roof of the building, which will constantly be measuring in real time the weather conditions outside the building. And that will include a camera, a spectrometer to measure the incoming spectrum of light, a pyranometer to measure the difference in diffuse and direct radiation that we're experiencing from the sun, which gets at how cloudy the sky is. And so we'll have a great amount of information about what light is being received from the building on the outside. And the idea is that then all the lights on the inside will be taking this information and using it to make decisions about what they should be doing in that moment, using those 4 channels I mentioned earlier. Okay, so this is showing an example scenario in the space that might occur around 10 a.m. where you see there's skylight coming into the space, there's ample daylight. The lights are probably still on because for comfortable vision, we do have to supplement that a little bit with artificial lighting, particularly on cloudy days, such as the one you see here. The kind of LED mix that we would use in such a scenario would incorporate blue light, so that blue channel that I mentioned earlier, which peaks at 480 nanometers, probably some mixture of both the warm white and the cool white channel, which is why you see this green and this orange curve here. And then also this 850 nanometer channel, which you can see peaking beyond the visible spectrum there. The reason for that is because daylight, of course, incorporates near-infrared light, and there's a lot of interesting research suggesting that near-infrared light provides some essential benefits for our well-being, our physiological health. And so this is one of the things that we wanted to do is try to incorporate this in the space so that we could study it and understand its effects a little bit better going forward. At 5 p.m., when the sun goes down and you get into the dusk hour here, very different things start to happen with the artificial lighting system. Of course, there's very little blue energy in the light at this time, especially around sunset and after sunset. So the lighting system will also replicate that. We've picked a warm white channel, which has very little blue energy, so that if we don't use the cool white channel and we don't use the 480 nanometer blue channel, effectively there's just very little energy in the blue part of the spectrum from the mixture of light that we're using. So you can see it's more or less following this pink curve here, which effectively shows you that pretty much the warm white channel is being used and no other light. And near infrared light is not used at this time because it wouldn't be a significant component of the daylight outside either. So we're trying to replicate as much as possible within, of course, constraints of what you might expect to be happening on the exterior of the building and try to bring it as much as we can to the interior. So at that point, I'll pass back to Virginie for a conclusion about designing lighting to promote better sleep.